Welcome to 7.2, where we're going to start looking at volumes. So in the last section, 7.1, we used a representative rectangle, if you will, to use this. And what we're going to do is we'll use the same process in the next sections, but we're not going to look at rectangles. We're going to choose a representative element and construct formulas to find our volume. So obtaining an integration formula and summing these representative elements up, the respective element will be a cross-section of S. Let A of X be the area of the cross-section. So before this would be like your rectangle, but now this is a cross-section representing the area of that region. And then what we're going to want to do is, just like we integrated the rectangle, we're going to integrate this cross-section. So if we give that cross-section a little width, we'll call it delta x. We will upgrade this to what we call a slab. All right, this slab is going to be equal to our delta x, and you can think of this as a slice of bread. The volume of our slab is a sub x sub I asterisk delta x. Again, this x sub I star or asterisk can be any location within that slab will work out fine. Adding the volumes of our slabs gives us a representation of, well, if we're going to call it a slice of bread, let's call it a loaf of bread, if you will. So our volume will equal the summation of all those slab volumes added together. All right, so what we want to be able to do now is we're going to take these slabs and we're going to need to cut them thinner and thinner and thinner and thinner until it approaches infinity. So if we do that, then we know that if we take our volume will be the limit as n approaches infinity of our summation becomes the integration from a to b of your area function times dx. And that's your volume formula. All right, so here we go. Our volumes of solids are going to be of a revolution. So volume, remember, is always a cubic unit. Solid means inside of a shape is all filled in. And revolution means formed by revolving a region in the two-dimensional plane about a line, which could be your x-axis or your y-axis or some vertical or horizontal line. So examples could be x equals a, x equals b, y equals c, y equals d, the x-axis, the y-axis, some line. So if we start to build this and say, let's take our two-dimensional rectangle, keep it simple, and we revolve this around the x-axis. The height of my rectangle times my width gives me the area, and we rotate it around the x-axis. So on the test, you're going to need to, when you draw these pictures out, I need to see this little circular arrow action going on here so I know where you're revolving it. And your rectangle is always perpendicular to that axis. So as we rotate this around, seeing that I'm from Wisconsin, we're going to get a big old wheel of cheese. And now your height, f of x, is now going to be called the radius of my circle. We'll call that capital R of x. And now we're going to find the area of this circle and multiply it by the thickness of our wheel of cheese, or we'll simplify it and call it a disk. So my volume will be the area of the disk times the width of the disk. Area of the circle times the width or thickness of our circle. So that will be pi times our radius, r of x function squared, times delta x. So imagine, if you will, here's my curve. And I want to go from A to B. So again, to build up your formula, think about putting little rectangles all the way inside of this shape. And now we spin it, and we get this disks all piled up on each other. Well, if we make these really thin, then the picture of my revolution for finding the volume of this solid would be just take the top function, think about flipping it over that line of revolution, there it is, and we'll draw a circle on the left side, a circle on the right side, and there will be our picture of our three-dimensional object. So again, just like we did with the slabs of bread, it's going to be our volume will be the limit as our number of disks approach infinity, the summation of pi times the radius function squared times delta x, which then turns into our integral, pi times the integral integrated from a to b of our radius function squared dx. Now, using your disk method, because you can have a horizontal axis of revolution, that's the one we just defined, but you can also have a vertical axis of revolution. So what's going to be important to remember is that this rectangle, again, always perpendicular to the axis of rotation. So now, whoops, come back here. So here, if we revolve it around the y-axis, now it's r of y. I have now a horizontal reference rectangle width of delta y, and we'll integrate it along the y-axis from C to D.